3. Next one. So I want to, in the next slide, I want to thank Andrea Grali and Dave Nielsen for the invitation to speak. Unfortunately, I could not come, and I'm very thankful for Andrea and David for allowing me to do this modern presentation from very far away. But I couldn't come. I really wish that I could, but I couldn't come this time. Maybe next time, physically. So in the next slide, number 4, I acknowledge people that have contributed to this work. Wonderful discussion with Jan Spielman, my postdoc Kanchan Sale, and my student Lihan. And since this, in the next slide, number 5, I just show quickly, since this is a multi-condensate, multi-band workshop, I just put quickly 2 works that I have done in 2-band superfluids. But today I will talk about something which is related to multi-condensates more than 2-band superfluidity. So on slide number 6, I show the outline of my talk. And as I usually do, I have like several topics which I go through, but I put my conclusions up front. So as you see there, I will just move to the next slide and put my conclusions, because of course we have a short amount of time. And here the conclusions in pictures show, and the basic idea is that I want to show to you is that the when I have a system with spin-orbit coupling and Zeeman fields in the context of cold atoms, I can have some parity violating superfluidity. And the top graph shows the possibility of having a system which is parity even initially. And if you just click on the next button, you're going to see on the momentum distribution on the top. Just click next. Not next slide, just next. Yeah. You can see a change in the momentum distribution, which goes from parity even to parity odd. If you go back and forth on the side, you can see a very funny effect. Andrea, could you go just back and forth a little bit to see that the momentum distribution is even in one case, is odd in the other case. And at the bottom panel, you would see first a plot of the quasi-particle energies, which is a multi-band structure in this case. And as you turn on an effective Zeeman field, which is transverse, which in the cold atoms complex corresponds to some detuning of a frequency, you see that these quasi-particle bands, they actually are not parity even. So if you click back and forth, you should be able to see that the density of states of the system changes with the appearance of additional peaks due to the fact that the quasi-particle densities and quasi-particle energies are not even in momentum. And so basically the message is that in the context of cold atoms, if you introduce artificial spin-orbit fields and artificial Zeeman fields, you can create states which are actually parity violating. Okay, on slide number 8, I put the conclusion in terms of words. It's basically saying that when I'm able, in the cold atoms context, to control the interactions, I can evolve the system from the BCS superfluid to a BC superfluid. But at the same time now, with the work of Jan Spielman, we can create artificial spin-orbit fields and Zeeman fields, and can induce several different phases in the system which are not possible typically in the context of condensed matter physics. And in addition to that, the ground state and some excitation properties of the system present parity violating situations. So in the next slide, number 9, I just show a little bit of the work that we have done before on topological superfluids, which was inspired by the work of Christian Volovic. In slide number 10, I just show to you the work that I'll be talking about is deeply rooted in those 3 papers. And in slide number 11, these are the main references for the talk. So let me go on then to slide number 12 to talk about the introduction to ultra-cold fermions, since the audience is very heterogeneous. There's people from condensed matter physics, people from cold atoms, and I want to sort of bring everybody more or less together the same wavelength. So on slide number 13, I ask you the question, why we study the cold fermions? So because we have a lot of interesting things that happen there, which are particular to cold atoms, but also can relate to atomic condensed and nuclear astrophysics. So in slide number 14, I just guide you through very quickly through what's one of the interesting achievements that happened in cold atoms, which was the tuning of interactions that was possible, which could take you from the BCS superfluid, which you have buried between K minus K states, but the interaction G showed on the right side of the slide here. It's much smaller than the Fermi energy typically. So it's a very weak attractive interaction in comparison to the kinetic energy of the system. And the chemical potential is essentially pinned to the Fermi energy. On the other hand, if you look at slide 15, you'll see that if this interaction is much larger than the kinetic energy Fermi system, then the system is essentially made out of very weakly interacting gas of very tightly bound Cooper molecules. So those guys essentially behaving really like bosons. They're not like any more Cooper pairs because the interactions are so strong in comparison to the kinetic energy of the system that those really are molecular objects. They don't overlap very much as Cooper pairs do. And in that picture, then the chemical potential of the system of two fermions is essentially equal to minus the binding energy of those two fermions. So in this particular case, the chemical potential becomes very large and negative, much below the bottom of the pen, and of course the system behaves more or less like bosons, so they can both condense. So if you click the next slide's goes, you're going to see those little fermions disappearing. Click several times until the bound state shows up. And then the chemical potential 2mu being equal to minus the binding energy shows up. So that's the kind of picture. So all these molecules then both condense into the lowest energy state, which is the binding energy of the system. In slide number 16, I just showed to you that in cold atoms context, the interactions between these fermions are typically contact interactions, and they can be translated into a scattering length, just using scattering theory, and that scattering length is dependent on the magnetic field. Basically because you can have two channels, a singlet and triplet channel, or a closed and open channel of the system, which are slightly different from each other by essentially a Zeeman energy. So when you change the external magnetic field, you can create a resonance between the closed channel bound state and the open channel scattering state. And that's how you control the interactions in the system. You apply a real physical external magnetic field, which you can tune, and then make the system have very strong attractions or very weak attractions, which means that the scattering length, let's say in the BCS regime, will be small and negative, and in the Bose regime, it will be small and positive. In slide number 17, I show you to roughly what the correspondence of the scattering length, how it behaves as a function of the attractive interaction, contact interaction. As I said, the scattering length is small in the BCS regime. There's a critical value G star for which bound states occur, two-body bound states occur. That's called the unitarity regime. That's the particular case, the scattering length divergence. And then in the BBC regime, the scattering length again is very small. The interaction G is very large, small and positive. So that's the preference that people have in cold atoms. Now, when you do this kind of analysis, I mean, already Leggett had showed a long time ago that you can have a situation in which the system, the ordinary BCS superconductor, slide 18, has a minimum when chemical potential is positive and large, which is essentially where the Fermi energy is. On the other hand, when the chemical potential is negative and large, say equal to minus 1/2 the binding energy, that minimum gap moves to k equals to 0. And now it's no longer controlled by delta, which is the order parameter, but by the mu square plus delta square and square root of all that. So it's controlled essentially by the binding energy in that regime, which means in order to create an excitation to the system, you have to break the pair. To break the pair now costs the binding energy in the extreme BEC regime. In slide 19, what we show that this case, when you go tune the interactions from weak attraction to strong attraction, from mu positive to mu negative, the system for S waves always remains gapped. So you have an indirect gap at finite momentum or a direct gap at 0 momentum. In slide 20, what I showed to you is just a picture of the BCS-BC evolution that you could have as a function of temperature and the interaction. At very weak interactions on the left, you see a Fermi liquid in the normal state. At very strong interactions towards the right, you see a Bose liquid. And in the superfluid state below the blue line, you're going to see a crossover between BCS superfluid to a Bose-Einstein condensation superfluid. And the unitary regime is here, and the lines separate the two regimes, BC, BCS, which is mu equals to 0, is also shown. As you can see, there's a smooth evolution in this case, so it was also probed experimentally. But I want to talk about something different. On slide 21, I want to talk about a situation in which you don't have a smooth evolution, but you have phase transitions, and most importantly, they have topological phase transitions. So on slide 22, I just remind you very briefly what a Lifshitz transition is, which is one of the first topological phase transitions were discussed in the literature a long time ago by Ilya Lifshitz, which is essentially a transition which involves a change in topology of the Fermi surface. As you increase pressure, for instance, in some systems like Bismuth, you can change the Fermi surface from a genus 1 surface to a genus 2 surface, in which a neck develops and breaks as a function of an external parameter, in this case, the pressure, the chemical potential. And so in slide 23, I just showed that in this kind of situations, you can also think of defining things which measure this topological change. And a typical thing is a topological charge, a topological invariant, like the Gauss law. You have a charge inside of a Gaussian surface of any shape. It doesn't matter what the shape of the charge is, as long as the charge is the same. When you enclose that surface, the flux through the surface. And so output is exactly the total charge. I mentioned briefly some topological invariants here. But the first natural thing to think about is that if you had a P-wave superfluid, and I choose a very simple one here, which has no line nodes, and delta is essentially linear in kx, so it's a px type superfluid. You can have line nodes along the equator of the system, but the excitation spectrum looks pretty much similar in 24, and this is slide 24. And you see this line of zeros showing up in the system, and of course this line of nodes in this particular case occur strictly in the BCS regime. If I now were supposed to change to slide 25 and change the interactions of the system, which effectively means changing the chemical potential from positive to negative in slide 25. In slide 25, yeah, good. So you can see that this excitation spectrum of the system, that Px, the fluid, has a line of nodes, right? And so in the BCS regime where the chemical potential is positive, the excitations are gapless. If I go now from, not from the equator, but now to the polar region, when theta is equal to 0, then a gap opens up in the excitation spectrum, so the system is anisotropic, as shown with the dispersion on top. However, when the attraction is very strong, you go to this molecular regime, which those guys define, the chemical potential becomes negative, and there's a full gap in the excitation spectrum, no matter what, if it's a P-wave state or not. So you still have to break a pair now to create an excitation to the system. So you can see that you can drive by tuning the interactions, or in this case, the chemical potential. You can go from a gapless superfluid to a fully gapped superfluid. So we can go to slide number 26, and that shows a possibility of a Lifshitz transition in P-wave superfluids, which is controlled by the interactions. And this just shows that there's a change in topology. You're going to have a gapless excitation, quasi-quark-holes touching when mu is positive, a little neck here at mu equals to 0, and then when it becomes negative, a full gap in the excitation spectrum. So this is the kind of topological phase transitions that one possibly could have in code M, slide 26. You can go to slide 26. And then 27, sorry. And then one could define in principle some topological invariants also, which are similar to the Gauss law, in which you can have the resolvent operator, and you have a flux through a multidimensional surface, and this N will be topological invariant, would essentially measure how many rings or how many rings you can have, or nodes you can have into the system. So in slide 28, I just mentioned briefly to you that there was a suggestion that we made in cold atoms that this topological phase transition could occur in P-wave superfluids. And they have some P-wave Feshbach resonances of P-wave interactions, but unfortunately the molecules that are created, the binding of the atoms, are not stable. So such topological phase transitions have not been observed. Then, of course, we know that if you have P-wave and you can tune the interactions from gapless to gapped superfluids, you can have such transitions. So we were wondering, how can we do this? And so we move next to slide 29. and show, well, this also could be accomplished by having systems with spin-orbit coupling. So on slide 30, I show that artificial spin-orbit coupling was created in the laboratory of Jan Spielman at NIST. And the basic idea here is that he was able to create something which involved a Raman process, and the Raman process would create for atoms, in case bosons and then fermions later, terms which involved Raman coupling, which is omega here. Omega here corresponds to essentially the intensity of Raman fields to counterpropagate beams that can create an excitation into the atom. And the delta here corresponds to detuning the frequency difference between two atomic levels. And Kx here and Krm is just the artificial spin-orbit coupling, which is due to the momentum transfer that Raman beams can impound into atoms. In slide 31, I just show very briefly how this thing is done. It needs a sort of rotation. So what this does is that if you look at the spin bases, you can have a spin up and spin down. Omega, which is the off diagonal of this little matrix, corresponds to the coupling between the spin up and spin down states. So that's the transition matrix elements that couple the two states. Delta is essentially the difference in frequencies between the laser light and the levels of the internal atomic states. And Kr is the momentum transfer in the Raman process. If you rotate these bases now on slide 32 do an SU2 rotation into the bases, which is a sort of a mix between up and down in the original case, you can rewrite this Hamiltonian basic as a spin-orbit Hamiltonian with Zeeman fields. Now omega moves from the off-diagonal part to the diagonal part. It looks like a Zeeman field. Delta, which is the tuning, also looks like a Zeeman field. And the momentum transfer due to the Raman process now looks like a spin-orbit field, but it's a spin-orbit field along the kx direction, which is the direction along which the momentum was transferred. So next slide, 33. It just shows briefly some comments about the nice work that Jan has done. In slide 34, I just rewrite that matrix into the standard matrix involving effective magnetic fields and the Pauli matrices. So the problem without interactions just becomes a momentum space two-level system, which we know exactly how to diagonalize. And when you do diagonalize in slide 35, what you see is that you have some generalized Alisti bases in which the energy of this up spin, the effective spin up, is essentially equal to the kinetic energy that we had before, minus the magnitude of the effective field, or plus the magnitude of the effective field. And that magnitude of the effective field is the sum of the three field components, which are now k-dependent, because we created this artificial spin-orbit coupling. In slide 36, I show the example of the Rashba spin-orbit coupling, which is better known in the context of Ness metaphysics, but that's not the one that has been created. In slide 37, I show then what is the type of spin-orbit coupling that is created. It's called of the class of equal Rashba Dresselhaus, which essentially has a component only along the kx direction. And this shows essentially what the profile of the fields on the left-hand side of this figure at the bottom shows what the profiles of the spin-orbit couplings correspond to. So it's essentially a very highly anisotropic spin-orbit coupling due to the fact that there's this momentum transfer of the Raman beams along only one direction. So in slide 38, then I show to you that in the current experiments, the spin orbit, the effective magnetic fields Hx of k are equals to 0. The component of Hy of k is equal to minus delta over 2, which is the tuning piece, and the spin orbit coupling that's induced along only the kx direction. So you couple the spin up and spin down, and the momentum that you couple to is only along the kx. And Hz of k is essentially the Zeeman field, which corresponds to the Raman intensity. So you can control the Raman intensity, which is omega. You can control the detuning of the laser frequency with respect to atomic levels, which is delta. And you can control V, which is the magnitude of the spin-orbit coupling. In slide number 39, what's realized experimentally, first we're going to look at the case of delta equals to 0, so which is essentially a case which I said preserves parity. If you look at that, the dispersions that you start with in slide 40 shows that if you begin with a quadratic dispersion and you have only no Hx, no Hy, but only the momentum kick, of course, which is not possible in a real experiment. You require the Raman field to be on, but just as a theorist you can analyze, you're going to move these two bands to the right or to the left along the kx direction. And then, of course, if I add now on slide number 41, a Zeeman field, which Hz equals to divided by EF. I just chose the kinetic energy. I can see now that this band split, the two bands that I had before split, and I have these two sort of helicity bands, and the energies are shown, expressions shown here, which are separated, and the green line shows exactly what the Fermi level is. So this means that if I add interactions, even in the S-wave channel, I can have intra and inter-helicity pairing, as I can see in slide 41. So if I move on to the next slide, then my non-interacting Hamiltonian has a very simple form. In a matrix form, it just has a kinetic energy, a parallel field, and a transverse field. And that transverse field, H perpendicular, is the one that contains the spin-orbit coupling in this null basis. So in slide 43, of course, I'll just go very quickly, it's just very, very basic stuff. You can diagonalize, you can find what the eigenvectors, that's a generalized helicity basis, and you have the energies are being generalized spin up, generalized spin down, which pairs up in slide 43. I can move on to slide 44. And I show that, that if you have finite tuning then, which means that now I have an external Zeeman field, I essentially bias those guys in one direction with respect to the other, because this transverse Zeeman field sort of tries to compensate a little bit the spin orbit. So without the tuning, without external Zeeman field along the y direction, where the spin orbit coupling is also present, it's y spin direction, you can see that the helicity bands are completely parity even, and they become parity odd. No parity when the detuning is present, which shows the two bottom curves. So if I move to slide 45, then I look at the momentum distribution of a standard system without any interactions, without any Zeeman fields. We can see just the Fermi function showing up on slide 45. However, on slide 46, if I add now the spin-orbit coupling, the momentum distribution in this highly anisotropic spin-orbit problem becomes very different, and they're shown here below. If you go to slide 47, now I'm going to add the transverse Zeeman field, HY, and you're going to see in the slide, if you go sort of back and forth between slide 46 and 47, that now the momentum distribution has changed. It is not anymore even in momentum space. And that has to do with the fact that the energies are no longer even in momentum space. So in slide 48, then I can show that I have a parity preserving situation on the left and a parity violating situation on the right. So if I put interactions in, which I'm getting close to the end, if I put interactions in slide 49 and 50, what I'm doing next is just add a contact interaction at the bottom, as I talked to you. I have a kinetic energy in the Hamiltonian, I have a spin orbit and Zeeman field, which are the same, and I add a contact interaction, as I described to you. And so, and in slide 51, what I look then first is the cases in which I look at pairing at zero central mass momentum. That's basically what the slide is telling me. I bring interactions back, and I'm going to focus now on momentum space at zero central mass momentum. In slide 52, then, this means if I write down my reduced Hamiltonian in that original spin basis, I'm going to have kinetic energies along the diagonal, along the off diagonal in the particle hole sector. I have the transverse fields, which are the ones that contains the spin-orbit coupling, and I have only S-wave interactions. Okay, particle-particle interactions. Okay, I have particle-particle interactions only along the S-wave interactions as represent.
So, Carlos, you have other 5 years plus 1 or 2 years for 2 questions. Okay.
Okay, sounds good. I'll finish up in 5 minutes. And you can see in this reduced form in the particle-particle sector, where the deltas are, delta 0 and delta 0, that interactions here are only in the S-wave channel. Okay, so now what I do, if I rotate to my generalized holistic basis, I can diagonalize my Hamiltonian. I can go to slide 53. And in slide 53, I can see that now I have diagonalized Hamiltonian in the particle hole sector. And at the cost, of course, of introducing a more complex structure in the particle-particle channel. Now I have triplet components and I have singlet components in the generalized holistic basis of the system. And since I mentioned to you before that the fact that if I had a triplet superfluid, I could have this topological phase transition. Now there is a chance, right, that by inducing this triplet component of the order parameter, due to the artificial spin-orbit coupling, that I can have topological phase transitions inversion as well. So if you can click on slide 53 and move on to slide 54, it just shows you, highlights first the triplet component. Now this triplet component here, there are two components, singlet and triplet components, and they add up, they remember that the interactions are from S wave. And this is just to show that the order parameter overall remembers as a triplet and singlet component that emerges into the system. So in slide 55, then we can exactly obtain what the excitation spectrum is, and the quasi-particle excitation spectrum, the quasi-Waldorf excitation spectrums, and the E2, the second one, can be 0. And so what we do, we classify the possible states that you can have on figure 56 according to the zeros of the low energy quasi-particle excitation spectrum. And in that case, depending on the interactions which you can do, and depending on the Zeeman fields which you can do, there are 4 types of states. One of them we call US2 that has 2 rings of nodes. Another one is called US1 that has one ring of nodes. You can see only points here, but there's rotational symmetry along K perpendicular in this case. And there's an indirect gap superfluid, and there's a direct gap superfluid. So if I put that into a phase diagram, which I'll show in 58, but in the next slide, 57, you can define topological invariance. So you're going to have I show the possibility of a transition, which is called topological, slide 58, which if you tune the interaction even by the system, you can go from a situation which you have nodal quasi-particles to a situation where you have no nodal quasi-particles, and it turns out that exactly at that point, at the transition, you're going to have Majorana fermions emerging. So let me go on to 59, and this Majorana figure 59. Majorana fermions occur exactly when you have the quasi-particle excitations are self-adjoint, and that's what 59 say. And then this happens at the phase boundary between 2 special topological phases. And in 60, I showed the phase diagram. If you go to the next slide, and this phase diagram here is just showing to you the Zeeman field versus interactions, and where all these different phases, US1, direct, gap, US0, are located. You can look on the left, on the right. This is basically indicating that as you increase the spin-orbit coupling, these phases, non-uniform phases or phase separation doesn't occur. Those phases become very stable. And just to, we can skip 61 and 60, go to 62. Just shows here the emergence of the strings. So we can move this one because I'm probably running out of time. And then if you add now the finite detuning, or basically the HY component of the Zeeman field, you can create also a phase diagram of the system. And those phases still exist. The 2-ring phase, the 1-ring phase, this is on slide 63. And 1-ring phase and 2-ring phase, and that's a plot of the HZ, the Zeeman field, along the XZ direction, along the Y direction, for at unitarity, or in the case of very strong interactions, for fixed spin-orbit coupling, which I fixed to 0.4, which is achievable experimentally. And so the phase diagram changes dramatically, and at unitarity you can see this. You can visit these 3 different phases by tuning the Zeeman field with Raman intensity, which is HZ, or the detuning HY. And in 63, we show that the momentum distributions in those particular cases, if you go to slide 64, you can see the momentum distribution when you have no, just a spin orbit coupling in the problem and the Zeeman field. You can see the disparity even on top, but when you turn on the detuning, you can have a parity, non-parity defined momentum distribution in the system. And that's all for the phase US1 who has ring of nodes. So I conclude now, just showing the density of states of the system. You can have the same effect without any kind of detuning. You have perfectly even situation that's at unitarity also, which is very strong coupling. When you add the detuning of the frequency of the laser beam, you create a state which is non-parity preserving. So I finish up here, and I put out the conclusions in words, and thank you for your attention.
We have just a few time. Somehow only a couple of questions. I don't know how to manage if Andrea.
Yeah. can repeat the question, perhaps. So we
Yeah,
ask
please
a couple
repeat the
of
question.
questions, we're going to repeat the
Any
question.
questions from the audience? Yeah.
Somehow,
It would be better if you can hear. Just to.
Well, I can speak up loudly. The lowest parity violating Y is the octopole. Is this octopole deformation here or in the momentum distribution? Maybe you could repeat it.
Did you get the question, Carlos?
Hear the question. Can you repeat yourself so I can hear it?
Thank you.
if you just said
Octopole.
Whether the momentum distribution is octopole-like.
If the
The
moment.
momentum distribution is octopole-like.
Mm-hmm.
True or not?
True or not? True or not?
Well, the momentum distribution, you're talking about the case of the case without the tuning or with the detuning? Without HY or with HY? The momentum distribution has all...
With the detuning. With the detuning.
Yeah, no, with the detuning, it's, you have all kinds of components. Not only showing the system, but the weights that they have in. I mean, can you put the momentum distribution for him to see for the detuning?
No, we are already changing the slides.
To the next one.
We are in
Okay,
the
so you have all kinds of proposals. When I have this thing here, and induce this px component to the orbit to the orbit parameter. That's the lowest order component, but you have all higher order components in the system
Okay, that's what.
coming out.
Okay, thank you. Other questions?
Distribution, you're going to have even an odd multiple component. So yeah, there will be an octuple component, but it's higher order.
Thank you. Any other question? If not, we stop here because we are out of time. So thank you, Carlos, for the conference at long distance. And I hope we can see you directly again very soon. Bye-bye.
Thanks a lot, Carlos. Bye-bye.
Okay.
we move to the next speaker, Alexander.